Understand and apply the intermediate value theorem. So first, we should probably, talk about the intermediate value theorem. Yeah, why not? It's in the title of the video. So what is this intermediate value theorem? Well, here it is in all of its glory and mathematical language. So we'll read through it first, and then we'll break it down a little bit into easier, understandable chunks. So the intermediate value theorem says let f of x be a function that is continuous on a closed interval a, b. Let L be any number such that f of a is less than or equal to L is less than or equal to f of b. Now, if those two conditions are true, then we can say that there is at least one number c in the closed interval a, b for which f of c is equal to L. All right, so that is the mean value theorem, but what does all of this mean? Well, the first thing that we need to point out is the very first condition. And the first condition says that the function has to be continuous, and not just continuous, but it has to be continuous on the closed interval a, b. And now when referring to this closed interval a, b, the a and the b are our x values or our inputs. So basically we're just saying the function is continuous on this closed interval, and the interval is represented by the x values, or by the horizontal axis. So left-hand side is a, right-hand side is b. Then we're going to let L be any number such that f of a is less than or equal to L, which is less than or equal to f of b. Well, since we're comparing L to f of a and f of b, we can say that L is our y value, or our output, or one could even say our height of our function. And then L has to be in between f of a and f of b. And that's what this compound inequality here says. Please don't think that it has to be, L has to be greater than f of a and less than f of b. L can be in between those two. This is just the notation we use. So L has to be in between f of a and f of b. So that means that f of b can be the smaller number and f of a can be the larger number. Alright, so again, if f is continuous and L is in between f of a and f of b, then there is at least one number c in the closed interval. So since c is in the closed interval, we can say that c also represents a specific x value or input. Now, what x value does it represent? Well, it represents the x value that gives us L. So basically, this f of c is equal to L implies that somewhere on this continuous function there's going to be a point c, comma, L, with c being the input and L being the output. C has to be in between a and b, and L has to be in between f of a and f of b. So great, boom, there's the immediate value theorem. But that's not really, it's very precise, it's very detailed, it leaves very little to the imagination. But it's not very helpful of what the intermediate value theorem actually does. So let's go ahead and let's take a look at the graph to demonstrate this. So what does the intermediate value theorem mean? Well, as you can see here, we have a graph. We have a, b. So we have our a and we have our b value. We can see the function is continuous on the closed interval a to b, meaning that it exists everywhere in between a and b. So it's continuous on a closed interval. And then we can see that our L value is in between f of a and f of b. So again, both our conditions are met. It's continuous on a closed interval, and L is in between f of a and f of b. And so all this is really saying is that if we have a point that's below this line L, such as this point right here, and if we have a point that's somewhere above our line L, what the intermediate value theorem says is that at some point in between a and b, this graph must intersect line L. And actually, let's put a point there instead of the highlighted part. So again, that's all the intermediate value theorem says, is if you have a point above a line and you have a point below a line, at some point you're going to cross that line. So for example, this point right here would be C comma L, because C is in between A and B, L is in between f of A and f of B. So again, this theorem is pretty obvious. Of course, if I want to go from point A to point B, I'm going to have to intersect line L. Duh. But it's really important in math to prove everything. And then we're going to take a look at why this is even helpful and why it was even worth proving. So let's also continue to look at the intermediate value theorem in different ways. So we can look at it here in a different way. So when I was 12 years old, I was actually 4 foot 10 inches tall. In high school, I had a very big growth spurt because, as you can see, at the age of 18 when I graduated, I was 6 feet 2 inches. So, as we can see, I grew 14 inches between the age of 12 and 18. And all the mean value theorem says is that at some point in time, between the ages of 12 and 18, I had to be 5 foot 6. Because it's impossible for me to grow from 4 foot 10 to 6 foot 2 without being 5 foot 6 at some point in my life. So the intermediate value theorem just says that I must have been 5 foot 6 at some point, but it doesn't tell us what age I was when I was 5 foot 6. It's just saying that I can't just jump past being that tall. At some point, I have to be 5 foot 6. And wait, there's another way to look at the intermediate value theorem? You better believe it. Alright, so let's say we do have our continuous function on a closed interval, so we know the graph has to exist between A and B, and the C value somewhere in between A and B. We also know that our L then has to be somewhere in between f of A and f of C. So what the intermediate value theorem says is that we're going to have a point CL somewhere in this boxed-in region. So if we did have a point CL, and we attach it to our awesome Triceratops right here, Tommy the Triceratops is free to roam anywhere as long as he stays in his little fenced-in area. Because in this fenced-in area, L is in between f of B and f of A, and C is in between A and B. So what the intermediate value theorem does is it kind of guarantees this patch of where our point can live, or Tommy the Triceratops is allowed to roam free. Now, one of the things about the intermediate value theorem that we haven't really touched on yet is the fact that it said there is at least one C value in between A and B for the given L value. And as you can see, the way that this graph is right here, we can see that there is one point of intersection between our graph and between our L value. So that is at least 1 point. However, if we were to move our L value up, again, we're still in between f of A and f of B, we can see that when it is at this height, there is 1, 2, and 3 intersection points, meaning that there would be 3 potential C values that would satisfy the intermediate value theorem. So just because we typically think of it being only 1 or at least 1, that does mean exactly what it says. There can be multiple C values because we're going to have functions like this, or we might have oscillating functions like the sine or the cosine function, which would have multiple intersection points. Next up, we can talk about applying the intermediate value theorem. Why is the intermediate value theorem useful? All right, so our first example, we want to prove that sine of x is equal to 0.3, has at least one solution on the interval 0 to pi over 2. All right, so let's go ahead and let's start labeling items in here. So let's see, sine of x we know is going to be our function, so sine of x will be f of x, and we want to prove that sine of x equals 0.3. Well, 0.3 here is a y value, so this 0.3 will be our L. And we want to prove that there is at least one solution on the interval from 0 to pi over 2. So 0 would be our A, pi over 2 would be our B, and then our one solution would be the C value that we're trying to prove exists. Now there's one thing I want to point out before we begin. Notice how the problem doesn't say find the C value. It just says prove that one exists. So all we're doing is proving one exists. We don't actually have to find that C value in this particular problem. Well, to prove a solution exists by the mean value theorem, we have to check our two conditions. Our first condition is f of x continuous on the closed interval, or is our function sine of x continuous on the closed interval 0 to pi over 2. And the answer to that question is, if we think back to pre-calculus and sine, well, sine is continuous everywhere. There are no vertical asymptotes, or holes, or jump discontinuities. So yes, sine of x is continuous everywhere. And yes, I need to state that it is continuous, and I need to state why it is continuous on this particular interval. I know that can be done in your head, but like in previous videos, we do need to write it down so we can demonstrate our understanding and knowledge of the topic. So again, is sine of x continuous on the closed interval? Yes, because sine is continuous everywhere. Our second condition asks us, is our L value in between f of a, so f of 0, and f of b, or f of pi over 2. All right, well, we already know what our L value is. We found that in the problem. So now we just need to figure out what f of a and f of b are, or what f of 0 and f of pi over 2 are. So let's see, f of 0 is going to be sine of 0, which is just 0. F of pi over 2 will be sine of pi over 2, which is equal to 1. All right, so now we just need to set up our inequality and see if it's true. Is f of 0 in between, is L in between f of 0 and f of pi over 2? Well, we just found out that f of 0 is 0. We know that L is 0.3, and we know that f of pi over 2 is 1. So now we need to ask ourselves, is 0.3 in between 0 and 1? And you better believe it is. So condition 2 is satisfied. And yes, I do need to see all the work that's on here, and I will need to see the conclusion I'm about to write. So since these two conditions are true, that means the intermediate value theorem is applicable here. So by the intermediate value theorem, sine of x equals 0.3 has a solution on the interval 0 to pi over 2. Because again, we're not trying to find that C value, we're just trying to prove it exists. And it does because our function's continuous on the closed interval, and L is between f of 0 and f of pi over 2. All right, for our next example, we are given that f of x is equal to x squared minus 2x plus 3, and we're being asked to determine the exact value of C on the interval 2, 4 that is guaranteed by the intermediate value theorem to result in f of C equals 6. Well, first thing here is that we know the intermediate value theorem is applied, so we don't need to check the two conditions. It says it's guaranteed, so we can assume that it works. However, we are trying to find the C value here. So let's identify a couple things. First, we want to figure out when f of c equals 6. So this time our L is 6. So we're trying to find the input value that gives us 6. So let's take a look. I'm going to take my function and I'm going to replace all the x's with c's because c is the variable we're looking for. So f of c is going to equal c squared minus 2c plus 3. And then the problem tells us that f of c, or our L value, is going to be 6. So 6 is equal to c squared minus 2c plus 3. Well, now this is just a simple quadratic equation, so we can subtract 6 from both sides to get 0 equals c squared minus 2c minus 3. We can then factor this to be c minus 3 times c plus 1. So that means c minus 3 is going to be 0, c plus 1 is going to be 0, so therefore c is going to be 3, and c is going to be negative 1. And woo! We're done. We found the c values that work because, remember, intermediate value theorem says there is at least one, and we have 2. But you might be asking yourself, why hasn't he boxed those in yet? Aren't these the solutions? And yes and no. Yes, they're the solutions, but we need to check if they are both solutions. Because remember, according to the mean value theorem, c has to be in between 2 and 4. And if we look at our c values, c equals 3 is in between 2 and 4, but negative 1 is not. So, yes, negative 1 would give us an L value of 6, but that particular c value is not guaranteed by the intermediate value theorem, so we cannot list it as a solution. Alright, for our next example, we're told the function is continuous on the closed interval 1 to 6. So boom, there's the first condition met for the intermediate value theorem. Then we're told the table below gives some of its values. Great. What is the minimum number of zeros that f of x is guaranteed to have by the intermediate value theorem? Alright, so let's take a look here. We're looking for the minimum number of zeros. So this whole zeros thing, this represents our L value. So we want to figure out when L is equal to 0. More specifically, how many times, or the minimum number of times, L can equal 0 on the interval 1 to 6. Alright, so let's just think about this. L equals 0 means the height is 0. And if the height is 0, that means we are looking for x-intercepts. So we are looking for x-intercepts. So let's take a look just at a random graph, and let's see what happens at an x-intercept. So again, just, a graph x-axis, y-axis here. And let's just say we have an x-intercept right here. Well, we know that in order to have an x-intercept, our graph has to go through that particular point. Which means, in this particular case, before we get to the x-axis, our y values are going to be negative. And then after we cross the x-axis, the y values are going to be positive. So it appears as though we know that we have an x-intercept when our y values change from being negative to positive. Well, if we look at another x-intercept, we can also have the case where we go down through the x-intercept, and in this case our y values are positive before the x-intercept and negative after. So from here we can conclude that zeros exist whenever our y values change sign. So, to figure out the minimum number of zeros of this particular function, we just need to figure out how many times the signs change with our y values. And we have to make sure that we're looking on our interval, so we are looking from x equals 1 to x equals 6. And let's see. Our first point is positive 3. That's positive. Positive 2, still positive. Positive 10, still positive. But then we switch down to being negative 3. So that means between these 2 points, we have a 0. Woo! And then between negative 3 and 2, it looks like we change signs again. So therefore, we have another 0. And then from 2 to negative 3, we change sides a third time. So therefore, based on the information we're given, the minimum number of zeros guaranteed by the intermediate value theorem is 3. And there we have it. So after analyzing the intermediate value theorem and what zeros meant, all we had to do was figure out when the y values change signs, and that indicated that we have a 0. All right, next up, we want to find the smallest integer a such that the intermediate value theorem guarantees that f of x has 0 on the interval 0 to a. So here we have another example that uses the word 0. So again, our L value equals 0. So in this case, we are looking for a change of signs in the y value. Another thing to notice is that we're trying to find the smallest integer a, which means that a has to be an integer. So 1, 2, 3, 4, so on and so forth. And we're looking over the interval 0 to a. So we want to find the smallest a, or we want to find the number that is closest to 0 that will guarantee that we have an x-intercept on that interval. So this is really just going to require us to do some test values. So now we can make a table here. We can do x and f of x. We know that our starting x value is 0. Well, the integer that's closest to 0, that is greater than 0, is going to be 1. So that's probably a value we should check. We could also check 2, 3, and 4, because those are all integers really close to 0, but greater than it. Well, now we're just going to plug all these x values into our function, and we're going to see what we get. So plugging the equation into my calculator, negative 2x cubed plus 8x squared minus 6x plus 7, go to the table feature and enter in 0, 1, 2, 3, and 4. So 0 gives us an output of 7, 1 gives us an output of 7, 11 gives us an output of 11, 3 gives us an output of 7, and 4 gives us an output of negative 17. Now again, since we're looking for a 0, we just need to look for a change of sign in the y values. So, no change in sign, no change in sign, no change in sign. But wouldn't you know it, we have a change in sign, which means that the smallest a value that guarantees there would be a 0 is 4. So therefore, a in this case is 4. And our final example, on which of the following intervals does the intermediate value theorem guarantee that f of x has a 0? Well, here we go again. We're looking for zeros, which means we're looking for sign changes in the y's, or in the outputs. And let's see, we're given 3 intervals, but also the option that none of the intervals give us a 0. So we're going to have to use the intermediate value theorem and compare the y values. So in our first interval, we can see that a is negative 5 and b is 0. So just like before, we can set up a chart, x and f of x, and we can plug both of these values in, so negative 5 and 0. Again, I'm going to use the graphing calculator to do the heavy lifting here. And when I plug in negative 5, I am going to get a negative 72. When I plug in 0, I'm going to get a 3. And if we notice the y values, there is a change of sign, which means there is an x-intercept, or there is a 0, over this interval. So this interval works. Woo! We'll circle that. All right, let's check out the second interval. So we'll do a similar thing. Our a is 0, our b is 3, so x and f of x, checking this guy out, 0 and 3. We already know when we input 0, we're going to output 3. And when we output 3, we're going to get negative 24. And wouldn't you know it, change of sign, woo! So that means there is a 0, or there is a point that L equals 0. So this interval also guarantees that 0. And then next up, a and b, so x and f of x. A is 3, b is 4. The output for 3 is negative 24. The output for 4 is negative 45, and unfortunately, wah wah, there is no sign change here. So therefore, 3, 4 is not an interval that has a 0. And since we've identified 2 of the 3 intervals, none of these is also not a solution.